Okay, so now we're going to use everything we've learned about enzymes in order to work out a mechanism of action. The protein we're going to look at is chymotrypsin, which is a protease. So it digests polypeptides at the peptide bond. And remember that the ways in which enzymes work, so enzymes speed up a reaction while not affecting the delta G of the reaction, the KQ of the reaction. And they work via kind of three mechanisms, at least in biological systems, either temporary covalent catalysis, oops, acid-base catalysis, or metal ion catalysis. And enzymes can use any combination of these in order to do what it do. And so we're going to go through that mechanism. It seems complex at first, but it isn't terrible. Um, and before we do that, I need to do a little organic chemistry review. And this is going to be very basic. Dr. Young would probably be ashamed, but it's enough to get us through um, the most of the enzymatic mechanisms that we do in a Biochem 1 course. And just remind us that there are nucleophiles and electrophiles. Nucleophiles are electron rich. Electrophiles are electron poor in some way. Nucleophiles tend to attack. And so this arrow refers to the flow of the electrons, and they tend to attack electrophilic species. And so nucleophile are things like the oxygen anion, um, the hydroxide anion, the nitrogen and the imidazole ring from histidine. All of those have these electrons that can attack these electrophiles. And electrophiles tend to be things like a carbon that's attached to a oxygen um, uh, ring and a carbonyl. So the oxygen is going to pull the electrons towards it, leaving that carbon as kind of electron deficient. Also, the carbon in a imine group or the phosphate in a phosphate group. And so, for our purposes, um, you can almost always get by if you don't know what a mechanism is by just looking for a uh, carbonyl carbon, right? So, almost 8 times out of 10, if you say nucleophilic attack of a carbonyl carbon, that's probably has something to do with the mechanism of action. So if you ever get lost, just go for that one. Okay, so we're going to go through the mechanism again. It seems complex, but it's not that bad if you just go through step by step. I'll say, as I said before, chymotrypsin is a serine protease, so it uses a serine active site serine for catalytic activity. And as we all know, that serine has a hydroxyl group. Now, and it's arranged in such a way that it becomes a very strong nucleophile. So many proteases, serine, chymotrypsin included, uses what's called a catalytic triad. Right, in this case, it's histidine, aspartic acid, and serine. And this kind of activates the serine to allow it to be a very strong um, nucleophile. If you mutate any one of these in the catalytic triad, you will lose catalytic activity. And so this is a look of how this catalytic triad is set up in the active site of the enzyme. Here you have the aspartic acid, Yeah, hydrogen bonds with this histidine that helps the histidine become a better proton withdrawing group itself. So this histidine then hydrogen bonds with the serine, and it is able to then pull off the hydrogen from the serine. Um, um, so that the serine becomes an oxygen anion and a very strong nucleophile. Now, if you remember from our amino acid structures, we typically don't consider serine to have an ionizable hydrogen because the pH at which you would actually get a loss of that hydrogen um, is too high. But in the presence of this histidine and this aspartic acid, you can actually make this serine ionizable, whereas in most cases or in normal cases it would not be. And so that's why you need this catalytic triad in order for action to happen. And so at the beginning of the kind of activity of the enzyme, you have this oxygen anion that is attached to the active site of this chymotrypsin that is simply waiting for the substrate to bind so it can do what it do. And so now we're going to say, kind of go through each of these steps. All right. So, so here we are. This is the active site of chymotrypsin. Again, aspartic acid, histidine, serine over here, right? The serine is going to be the nucleophile that actually attacks the peptide backbone. This is the active site here. And there are a couple of other features that are important. There is a oxygen anion hole, and so this is a place that helps stabilize some of the oxygen anions that are going to be formed in the process of this activity. And then there is a hydrophobic pocket. And we will see that pocket is necessary for the specificity of chymotrypsin. Chymotrypsin only cuts next to um, aromatic amino acids. So they cut the peptide bond of aromatic amino acids, and we know what those amino acids are because at this point we know all of the structures of the amino acids. And so clearly the aromatic amino acids would be what? Right. Um, okay, so here is the polypeptide binding in the active site. And note, here's an aromatic amino acid, and we can look at that and see that it is phenylalanine, and it is positioned in such a way that the carbon of the peptide bond is positioned right next to this serine that will be the nucleophile, right? So the hydrophobic pocket allows for the peptide to be positioned right where it needs to be so that the serine can attack this electron deficient carbon in a carbonyl carbon and begin its action. And so at the start of this, everything is set up. You bound your peptide into the um, active site, and we are ready to go. Now, the first step is this nucleophilic attack of the peptide. And so what happens here? The hydrogen gets withdrawn to this oxygen to the imidazole group of the histidine. The oxygen comes in. Let me just blow this up. The oxygen comes in and attacks the carbonyl carbon of the peptide bond. You can see NHCO. Right, so that's the peptide bond that's right next to this phenylalanine. That forms a covalent bond between the serine or the enzyme via the serine and the polypeptide. So here's an example of covalent catalysis, right? You form a temporary covalent bond between these two things. You also um, have in breaking this bond, you have this hydrogen uh, come, uh, you have a new bond formed with this histidine over here. And so here we are um, um, from step one and before, you have formed this covalent bond between the serine and the carbon of the peptide bond. You then form an oxygen anion. This would normally be unstable, but it is stabilized by hydrogen bonding within the oxygen anion hole. So this is the intermediate or the transition state of this particular enzymatic uh, reaction. This is not something that's stable, but because of the oxygen anion hole, it's stable enough to allow for this to go forward. The next thing that happens, or that happens at the same time, is that we break, we break this bond and we break that bond, right? And so you're pulling off uh, this hydrogen and breaking the peptide bond over here. Now, histidine is now donating hydrogen, so that's an example of general base catalysis, right? It's donating hydrogen to the substrate, and so um, that's going on. So now you formed a product here. You've clipped the polypeptide. Half of it has gone away via this NH2, and you're left with what? A deprotonated histidine. You have half of your polypeptide that is still covalently attached to the active site of the um, enzyme. Um, So you've already done the cleavage, right? So you've done the protease action. The only thing left to do now is to restore the enzyme to its original state by somehow breaking this covalent bond between the active site and the substrate. So here we use specific acid-base catalysis, and we have a molecule of water that comes in. That water becomes a nucleophile that attacks this carbon once again, attacking the carbonyl carbon of the um, uh, uh, or the carbon of carbonyl carbon. This is going to reform an oxygen anion. That oxygen anion will be stabilized by the oxygen anion hole so that you form another intermediate. Again, this is our prototypical tetrahedral intermediate in which you have this carbon that is bound to this oxygen. It's formed this oxygen anion here that's stabilized by the oxygen anion hole. And then this is going to collapse. The oxygen anion is going to reform the carbonyl group. And in doing so, it's going to break the bond between the enzyme and the substrate. Uh, when that happens, you'll also um, reform the bond between the now protonated histidine and the serine group. And so that's shown here. Now, um, so this is where we were with this intermediate. And so now you have released the substrate from the enzyme. The substrate is now free to float off. You have restored your original serine. You still have your histine and your aspartic acid that are ready to go for the next go round. And so here we have restored the enzyme to its original function, and it is ready to pick up another polypeptide and do the whole thing over again. And so we can see in chymotrypsin that uh, it uses Acid-base catalysis, it uses covalent catalysis in order to accomplish its goal, which is to clip this protein, this polypeptide, and then restore this enzyme so it's available to clip another one. Again, and there it is, mechanism of chymotrypsin. Congratulations, you just got through it. I'll just say kind of one more thing, which is that the specificity is determined by that hydrophobic pocket. So in chymotrypsin, it has this pocket that has things that allow for the binding of aromatic rings, tyrosine in this case, phenylalanine, so forth. Simply by changing this pocket, you can change the specificity of the enzyme for the peptide bond. And so for chymotrypsin, it binds preferentially next to aromatic rings. But if you do something like put in a negatively charged amino acid at the bottom of this pocket, you're going to attract instead um, uh, basic amino acids, right? And so here, trypsin does the same thing. It uses the exact same mechanism, but it just cuts next to basic amino acids um, and not aromatic amino acids. And then if you put something that's relatively large and hydrophobic there, you can preferentially cut next to relatively small hydrophobic molecules like alanine. So here, but you can keep the same basic architecture in place and simply change the hydrophobic pocket, and you can change the specificity of the enzyme for the polypeptide. Okay, so I'm going to stop with that mechanism, and then we'll move into kinetics next week.